All right, guys, so we're back, and now we're working on question number 4 on the review. So it says a 0.5 kilogram ball is being dropped from a height of 7 meters. So they tell you the height, they tell you the mass. We want to know what's the gravitational potential energy of the ball. So that's just GPE, pretty straightforward. This one, it gives you all the elements, so it's just going to be mgh. So it's just 0.5 times the gravity constant, which we're making the assumption it's on the Earth, so 9.8, and then 7. So if you multiply all those out, you should get something like 34.3 joules. So that is how much energy the ball Earth system has to start. And that would all be gravitational. So if you imagine this up here, if this is point A, because that's the question that we're at, part A. So at part A, it's all GPE. For part B, it says how fast is the ball moving when it hits the ground. So it's going to fall. And we've talked about this. So as it falls, it speeds up. You could do kinematics with this too, but I'm going to use energy because I think it's easier. And at part B, all this GPE is converted into kinetic energy. So it's just using conservation of energy. So this 34.3 in part B is now all kinetic energy, which is just the equation for kinetic energy is 1/2 mv squared. So 34.3 equals 1/2, and then the mass was 0.5, and then v squared. So half of a half is a quarter, so you're going to divide by 0.25 on both sides. So that'll drop out. And then again, you have to take a square root. You do this a lot. So we'll take a square root and solve for v. So if you do that, you should get the velocity as it's running into the ground something like 11.71 meters per second. So that's your answer to part B. Part C says if the ball has a spring constant of 1500 newtons per meter, so that's like the elastic constant, K. That's our K value. We want to know how much will it be compressed when it's in contact with the ground. So basically, we're looking to see how much the ball gets squished. That's another way you can do it. Again, it's just conservation of energy. So spring constant, things getting compressed or stretched, that's EPE, and the formula for that is 1/2 kx squared. And we're looking for x, how far it's stretched. Our elastic energy is the same as the energy that we started with, so we're going to assume that all that energy is converted into that. So 34.3 equals 1/2 15,000. And then x squared, x is the compression, so that's what we're looking for. So 7,500 is half of 1,500, so we're going to divide both sides by that. So those drop out. And then we're left with very similar to what we have over here. We got to take a square root because we want x, not x squared. So when you do that, you get x is equal to, for this one, 0.0676 meters. So about 6 to 7 centimeters, which is probably pretty accurate for a ball, even if it's like a big ball, like a basketball. It doesn't compress that much. The last one says, if the ball rebounds to a height of 4 meters, how much energy was transformed into heat and sound? So so when it bounces up, it does not bounce as high as what it originally was. So it's down here now, and the height's only 4. So at this point, it's got GPE. It's at the highest point, so it stops. So there's no kinetic. It's not stretched or compressed anymore. So we're going to compare these GPEs. Obviously, in A, it's bigger than it is in part D. So the difference in those energies should be the non-mechanical. So again, conservation of energy idea, this is part D. The gravitational potential energy in the beginning, so I'm going to say that's at part A, should equal the gravitational potential energy at D plus whatever non-mechanical energy, heat, sound, all that is there. So again, we already know a lot of these numbers. So this is the 34.4 or 34.3. That's the energy I started with. We're going to basically do the same thing up here, except plug in 4 instead of 7. So when you do that, you should get a value of 19.6. That's what 0.5 times 9.8 times 4 is. So 2 times 9.8, yeah, that works out. And then the non-mechanical energy is the difference between those, so you just subtract and solve for NME. So I'm going to take this to the other side and subtract it. So you get the non-mechanical energy is equal to 14.7 joules. So that's how much heat and sound was generated during that collision with the ground. So that's number 4. Continuing on, 5 is a momentum impulse problem. So a mass of a ball. The ball is originally traveling at positive 12, so this is like VI going towards the wall. And then VF is when it comes off the wall. That's when it bounces off. And it tells you that those are the values here, so positive and negative. A, what's the momentum before it hits the wall? So again, momentum is pretty straightforward. P equals mv. We're looking for the initial. So that'd be the mass times the initial velocity. So it's going to be 2 times positive 12. So that's just 24. So a positive 24. The unit for momentum can be kilograms, meters per second, or Newton seconds, depending on what you want to use. Same thing. For part B, it wants to know what's the momentum as it bounces off the wall. So we're looking for the final momentum. So it's the mass times VF. So it's still 2, that's the mass, but this time it's bouncing off and it's going -6. So 2 times -6 is at -12. Same units, kilograms, meters per second. Part C, we want to know the impulse. So impulse is the change in momentum. So we're just going to subtract final minus initial. So PF minus PI. So when you do that, it'd be -12 minus 24. So that's going to be a -36 kilograms meters per second. And then finally for part D, it says what force does the wall apply to the ball if they're in contact for 0.04 seconds. So 0.04 seconds, that's our time or change in time. We also have our impulse equation is the force times the time. So if we solve for force here, we divide through by time on both sides. So I'm just doing the algebra before I plug in the numbers. But you could plug in the numbers too. So it's going to be -36 divided by 0.04 is going to be our force. So when we do that in the calculator, you get something like -900 newtons. And it's a negative force. That makes sense because like the wall is pushing back to the left, so the direction of the force is definitely going to the left from the wall. Okay. Another momentum, conservation of momentum question that we got is a 2 kilogram block is moving at 6 meters per second to the right, so that's like this one, and a 5 kilogram block is moving at 2 meters per second to the left. That's this one. That's before the initial collision. And then afterwards it says they bounce off each other, and it says that the 2 kilogram block is moving to the left at -1, and we want to find what is the speed and direction of the velocity of the 5 final. So we're looking for that final velocity, and then we're going to calculate the energies before and after, and then from those determine the type of collision. So for part A, I'm just using conservation of momentum, so the total momentum initial should equal the total momentum final. That's that part. And then it's just like for each piece that has momentum you're going to solve. So for the first one, it'd be 2 times +6. Because that's this piece, and that's supposed to be a 6. Let me redraw that because it's pretty incomprehensible. So that's 2 times 6. There we go. And then we're going to add, because sigma means add, the momentum of this one. So this would be 5 times -2. And that should equal, at the end, it's 2 times -1. And then for the 5, we're not sure about its velocity, so I'm just going to say 5 VF. And if you labeled this like A and B, you could say VFB. That's fine. So we'll call that second object B and the first object A. So it's just plugging in and doing the math. So 2 times 6 is 12, plus 5 times negative 2 is negative 10, equals negative 2 plus 5 VFB. Again, we're going to take the 2 over here. So this is like 2, and I'm going to subtract a negative 2, so I would add 2 to this side over here. So this is like 2 plus 2 is 4, so I got 4 equals 5 VFB. And again, just doing the algebra and finishing it up, you divide through by 5 on both sides. So VFB is that the positive 0.8 meters per second. So so after this collision, this guy moves at a small velocity going to the right. That's what our numbers say. For part B, we're going to find the total kinetic energy before the collision. So I'm going to add up all the kinetic energies of all the pieces before its initial. And for part C, we're going to do the same thing, but it's after the collision. So it would be KE final or K final. So we're going to do the kinetic energy equation, which is 1/2 mv squared for each piece. So it would be 1/2, the mass was 2, the velocity was 6, and we're going to square that. And then for this B part, it'd be 1/2, 5, and then 2 squared. So again, I didn't write out the equation for kinetic energy, but I'm assuming you guys got that down pretty well now. So, so if I do this, you get 46 joules for the initial. And then plugging in for the afterwards, it seems like everything is slowed down, so there's going to be less kinetic energy. So it'd be 1/2, 2, and then it'd be negative 1 squared. Oh, I could put the negative in here for the 2 if you want. When you square it, it goes away. So you don't really have to worry about the negative when you have the kinetic energy equation. And then for the second one, it's 5, and then 0.8 squared. So if you put all those in your calculator, you get something like 2.6 joules. And you can see that those two values here, 46 and 2.6, they are not equal. So since they are not equal, that means that it is an inelastic collision. And the reason why it's inelastic is because the kinetic energy initial, the total kinetic energy initial does not equal the total kinetic energy after. So that means it's not elastic, because if it was elastic or E-type collision, they would be the same number. And the other piece of information that's important is they don't stick. So if they're not sticking together, then it is just regular inelastic. If they do stick together, that would be perfectly inelastic. So, so that's that problem. All right. I'm gonna maybe do one more question here with torque, and then I'll make a third video for the other one because I don't want them to get too long because they can take a little bit. So it says a 5 kilogram object is placed on the 0 mark of a 3 meter long stick of negligible mass. So we don't have to worry about the mass of the stick like you would in real life, like you did for your lab, but we have a 5 kilogram object placed here in this box. The stick is being supported at its midpoint, so if this is 0 and 3, this is 1.5. So this distance from 5 to the point of rotation here is 1.5. We are trying to figure out where to place the 8 to make it maintain rotational equilibrium. So this would be our kind of our setup. That's our picture for A. For part B, if we're in rotational equilibrium, that means the sum of the torques equals 0. So if you add up all the torques, you get no net torque. So that means that the torque from the 5 on the left side, which is going kind of that way, has to equal the torque from the 8 on the other side. So it's kind of the seesaw problem. We've done this a couple times before. We're going to use RF sine theta for this equation. Just reminding you, if everything is balanced, that means that the lever arm is perpendicular to the gravity force, which is straight down. So that's going to be sine of 90, which is going to go to 1. F is mg, because that's the weight. That's the weight of both of them. So again, for the 5, it would be like R mg for the 5 side. So for all the 5 information. And then on the other side, it'd be R mg for the 8 side. So and I'm just making little subscripts here. There's a G on both sides, so we can drop that out. There's an M on both sides, but they're different masses. So we said that 1.5 is how far away the 5 is. So it'd be 1.5 times 5 equals, the G's dropped out. We don't know R8, so that's what we're looking for. So R8. And then the mass of the 8, which is 8. So, so we're going to divide through. And if you do 5 times 1.5, that's 7.5. So 7.5 equals R8 times 8. And then you divide through by 8. And you'll get a number that's slightly less than a meter. So it's like 0.5 or 0.9, excuse me, 375 meters. So that is the distance it is away, 0.9375. So it's going to go like here. Or maybe in here somewhere. Okay. And that's what you need to do to get it to balance. See, it says where's the location on this stick. So you're going to try to figure out where this is. So if this is 0, we're trying to read what that is. So I'm just going to add 1.5 to that number. So plus the 0.9375. And if you do that correctly, you should get something like 2.4375. So that is the actual place on the stick where you would need to place this 8 kilogram block in order to maintain rotational equilibrium. So that one's just more of a conceptual idea. Again, not a ton of math there. You're just figuring out what point on the stick it is. Okay. So I'm going to actually do 8, and then maybe we'll just keep going because there's too much left. So there's this tub washer. It tells you the moment of inertia of it. So like your washing machine at home or at a laundromat. It's going to go into a spin dry cycle. So it starts from rest, so it's not moving, and then it starts spinning, and it tells you the acceleration and the time, and it says it starts from rest. So this is just kinematics. How many revolutions does a tub make? So with kinematics, it's just angular or rotational kinematics. So delta theta, we're looking for how many times it goes around. So that's theta. Omega I, it said it was at rest, so that's 0. Omega F, we don't know. Alpha is the acceleration, that's 30.8. It says rads per second squared or rads per second. And then the time is 7.1. So we have enough information. We have 3 out of 5. We're looking for theta. So we're going to use the one without omega F. So for part A, I would use delta theta equals omega I t, or delta t, plus 1/2 alpha delta t squared. This first term goes away because 0 is the initial speed. We're looking for delta theta, so that's the thing I'm going to use. 1/2 alpha is 30.8, so it's just plugging in the numbers. And then 7.1 is the time, and make sure you square it. This answer, which I will write out when I put that in my calculator, I got something like 776.314 rads. We don't want rads, we want revolutions, so we're going to have to convert a little bit. So I'm going to take that, and there are 2 pi radians per 1 revolution. And that's what we're trying to get into as revolutions. When you divide, make sure you put 2 pi in parentheses or divide by 6.28. That would work as well. But your delta theta answer in the correct unit for revolutions is something like 123.55 revolutions. Okay, so that's your answer to part A. For part B, it wants to know what's the final angular velocity of the tub, so we're looking for omega F. Again, you just pick an equation that you think is the easiest at this point because you have all the numbers that you need. So I used this one. And again, the initial velocity is 0, so that just goes away. So it's just 30.8 times the 7.1. And if you do that properly, you should get 218.5 0.68 or 0.7. And rads per second is fine for this. It did not specify that you needed it in revolutions per second or revolutions per minute or anything like that. Okay, so that's B. Part C wants to know what is the net torque acting on the tub. So the net torque is I times alpha. So Newton's second law, essentially. They told us I, they told us alpha, so it's really just plugging in again. So I is the 0.24. Alpha is the 30.8. So it's almost a quarter of 30.8. So you get like 7.632, and that would be meter newtons. So that's your answer for that one. All right, so two more. These last two are dealing with simple harmonic motion type ideas. So it says an unknown mass, unknown mass of 20 newtons per meter is on a 20 Newton per meter spring, so that's K. And it makes 72 oscillations in 180 seconds when it's stretched from its maximum displacement of 0.07. So I kind of drew this out. So the amplitude is 0.07. That's your maximum displacement. And it's going to oscillate. And it says if the mass starts at the positive amplitude, so I'm starting over here, and it's going to oscillate back and forth and back and forth. So for part A, I want you to find the period of oscillation, which is T. So the period of oscillation is the time divided by the number of oscillations. So we had 180 seconds, and we're going to divide that by 72 oscillations. So for one oscillation, it should take you very close to 2.5 seconds. So if I drew this out, 0 seconds, this would be 2.5. Half of 2.5 would be 1.25. And it kind of oscillates through those times. So this is like 0.625. And this would be like 1.875. Okay, so that's like your times at different positions. So we did part A. Part B is the frequency. So frequency, just take the inverse of the period. So they're just 1 over capital T. So it'd be 1 over 2.5. So if you do that, you get 0.4 hertz. So the last part, or the last couple parts, C wants to know what's the mass. So we know the period, and the period equation for a mass on a spring is 2 pi square root of m over k. So again, we're just looking through to find for m this time, we know this is 2.5. I'm going to keep that as 2 pi. M is what we're looking for, and then k is 20. So we're going to square everything. So if we square both sides, it'd be 2.5 squared equals 4 pi squared, because I square each one of those terms. And then the squared and the square root are going to cancel out, so you have m, and then it's over 20. So again, you're just going to take this whole thing and move it to the other side, and you do that through division. So it'd be like 2.5 squared, and I'm not doing any of this math out on the paper here, I'm just showing you what it should be, times 20 divided by 4 pi squared. Let your calculator do the heavy lifting, and that's equal to m. So that's the mass. And when you do that, you should get a mass of something like 3.17 kilograms. So that's the mass of the block that is on this oscillator. And then finally for part D, they tell us to evaluate and try to find the position at x is equal to 3.8 seconds. So this is that amplitude times the cosine. So the amplitude's 0.07. Cosine of 2 pi f, we know f, so it's going to be 2 times pi, little multiplication symbol there. F is 0.4, and then we're going to multiply it by the time that we're evaluating at. It's 3.8. Remember, for this calculation, you got to put in radian mode. But if you do that, you should end up with like negative 0.0694 meters. So it is almost at the negative amplitude, and that should make sense, right? So it's 3.8. So if you did 2.5, that's one complete cycle. Then you start here at 2.5. If you add 1.25 to 2.5, this is at, so if you add a whole another 2.5 to it, you're at 3.75. So that's the maximum negative amplitude is here. And then it's just 0.05 seconds more, so it's just moved a little bit back this way. So you're very close to the negative amplitude, which should make sense. So again, just evaluating your answer at the end to make sure it makes sense. Let me go ahead and get through the last one here, number 10. 10 is a simple pendulum problem. So again, you got a pendulum, a mass swinging back and forth on the rope. It tells you the length of the pendulum. It tells you the mass. It says it's given an initial speed of 0.96 meters per second at its equilibrium. So they started off by pushing it, and that was its speed. So part A wants to know the period. So the period of oscillation for a pendulum is 2 pi square root. Pretty close to the spring one, but a little bit different. It's L over G this time. So that's an L and that's a G. So 2 pi square root. L is the length, so that'd be 2.23. And we're going to divide that by gravity on Earth, which is 9.8. If you do all that, you should get something really close to 3. It's like 2.997 seconds. So that's how much time goes by. For part B, it wants to know what is the total energy of this system. So if we did that, the total energy is actually the kinetic energy at the bottom, because at the equilibrium position there is no height. So the kinetic energy, which would be 1/2 mv squared, so you just plug it in to 1/2. The mass is 6.74, and the speed that it was moving at was 0.96. And you got to square that because it's 1/2 mv squared. So the kinetic energy, which is the total energy, is something like 3.105. You could use kinetic energy and the total energy to figure out like how high did it swing up to, and you could find the angle and do other things, but I didn't ask you to do that in this problem. But you should be able to. It's just conservation energy. Finally, it asks you, if we assume the motion begins at a positive amplitude, which is 0.464 meters, what's the location of the pendulum when it's at 5 seconds? So again, this is our position as a function of time. We're going to evaluate it at 5 seconds. It's the same equation. So A is the amplitude, which is the 0.464. Cosine 2 pi. Again, got to be in radian mode. The frequency is the thing that you need to figure out. So if the period is this, the frequency would be the inverse of that. So it'd basically be 1 divided by 3. I'm just estimating it here. So that's like 0.33, close to that. When I did it with the actual number, it was 0.334. So times 0.334. And then I need to multiply it by the time that we're evaluating it at. So when you put that in your calculator, you get something like negative 2.235. I'm sorry, I put the decimal point in the wrong spot. So it's still negative, but it's 0.2235. So if I think about this, is the positive amplitude is 0.46, this is the negative amplitude, negative 0.46, so it's somewhere in here. So let's just evaluate that. So at time equals 0, that's when we start. 1 complete oscillation is 3. 2 complete oscillations would be 6. So if it's 3 to go across, this is 1.5. So 0, 1.5 is here. This would be 0.75 seconds. So if I do 3 and 1.5, that's 4. And then 4.25, sorry, 5.25 would be at this point, kind of just tracking through. So yeah, it makes sense that it's over here. It's got some negative amplitude in terms of meters, and that is it. So guys, that's the whole review. Good luck. I will talk to you guys later. Be well.